99% of the beam to be connected with slab. Part of this slab together with the beam will make something called T section. How much part of the slab will make T section? We have something called B effective flange width. Effective flange width. We have 3 values, and we are going to use the least value. Span of the beam divide 4. 16 slab thickness plus web width. Here is the web width. Or center line to center line, and be careful about this point. Center line to center line. So go ahead and get this value and use the smallest value. If the beam at the edge of the slab, it can be L section, and we have flange width. Part of the slab will work with this beam as flange. To figure out this value, this width, effective flange width, we have 3 values. It's different than this case. Here you are talking about intermediate beam. So we have a slab on right and the slab on left. But if you have edge beam, we have only slab from right or one side only. So we have a little difference in these values. Okay? First case, first scenario, nothing changed, nothing different. If the neutral axis within the flange thickness. So we have capital C, and this value is B effective. We have capital T. Both of them are equal. So I can figure out the depth of neutral axis or depth of stress, and be sure that this depth A smaller than the thickness of the slab. That means I assumed the correct position of neutral axis within the flange. Then your nominal moment and the design moment can be done. And we solved one example. Second case, the neutral axis out of the flange. So I'm going to divide this cross section. Remember, we have a steel reinforcement at the bottom. Area steel. We have part of the cross section at the top above the neutral axis under compression. So I'm gonna divide this cross section to 2 parts. First part is this part of the cross section and this part of the cross section with a little bit of this area steel, not all of area steel, but a little bit. So we have area steel flange with this part and this part. Remember, I can figure out the total width for the cross section, be effective. And this width, I can figure it out. Can be assumed or it's given. So this width plus this width, I can figure it out, will be B effective minus B web. If you subtract B effective, the total width, minus this width, the web width, I can figure out this one plus this one. Any questions so far? Okay, and we have a little bit of this area steel. this area steel will be divided to two parts. The first one, area steel flange. Here. So I'm gonna assume we have tension and we have compression. This compression force equal 0.85 F prime C, the width time the thickness, this thickness. And which width? This one plus this one. So it will be B effective minus B web. I can figure out the value of this compressive force because everything is known. The tension force in the steel reinforcement that I cannot know how much. I told you this total area steel will be divided to two parts. The first part is unknown. I don't know how much. A little bit, but how much I don't know. So the tension force will equal this little of area steel flange times F field, as we know. For equilibrium, T and C must be equal. So C equal T. If you equate this equation with this one, the only unknown will be the little bit of the area steel flange. So first step, first part of the cross section, I can figure out how much steel reinforcement here is working with this part of the cross section. My question is, if you know this part of area steel, anybody can know how much remaining? I will assume the remaining area steel web. How much? Guys, remember, this part of area steel plus this part of area steel equal the original part. The original part is given. And from step one, I can figure out this part. Can I figure out the remaining? Yeah, you can. You can. Area steel web, the remaining part of area steel equals the original part of area steel minus area steel you figured out from step number one. The second part of the cross section, this part of concrete and the remaining area steel. So we have this part with depth A. This depth to the neutral axis will be A. And the remaining part of area steel. Right now, I can figure it out. So we have tension and we have compression. This compression equal 0.85 F prime C A B web. This tension force equal area steel web, the remaining area steel, this one, time F yield. Both of them are equal, so I can figure out the value of A. Remember, from the first step, I can figure out the nominal moment. One of them times the distance in between. From the second part, I can figure out the nominal moment. So I'm gonna assume this one flange and this one web. One of them times the distance in between. Once you get Mn and Mn from the first part and second part, the final nominal moment for the whole cross section, both of them must be added together. If you decide to get the design moment, go ahead and multiply this number by phi, which equal 0.9. Let me do an example to understand what's going on in these calculations. We have example. We have this example. We have a T section and the effective width is given 30 feet. So I don't need to search for what is the value of P effective. No, it's given in this problem only 30 feet. I'm sorry, 30 inch. F prime C 4,000, F yield 60,000. We have area still given. How much? 8. Number 10. The area still total given also 10.12 inch square. And as the centroid of this reinforcement, we have depth 30 and the flange thickness 4 inch. My question is, do you think neutral axis within or outside the flange? Remember, we have two cases. Probably the neutral axis within the flange, probably the neutral axis outside the flange. So what do you think? I don't know. I will assume neutral axis within. It's more easy. So I'm gonna assume it first. That means I assumed neutral axis is here. Probably I am wrong. Let's see. So we have compression on this part, capital C equal 0.85, F prime C, B effective A. And we have tension in this steel reinforcement T equal area steel times F yield. For equilibrium, these two forces must be equal. So 0.85, how much F prime C? 4,000. B effective 30. What is the value of A? Unknown. A, this depth. Equal area steel, how much? 10.12. F yield, how much? 60,000. Go ahead and find A. How much A? Let's see. 10.12 times 60,000 divide 0.85 equal 5.95 inch. Can you see something? This distance equal 5.95 inch. How? It doesn't make any sense because this thickness, the total thickness is 4 inch. Can you see? 4 inch. So A greater than slab thickness. Your assumption is not correct. Neutral axis is outside the flange. So you have to use this case. So if you have T section, I will assume first we are in the first case, which is your neutral axis within the flange. So we have to check area A smaller than H flange. If this happen, go ahead, you are good. You are correct. If this not happen and A greater than flange thickness, you are in this case. So we are in this case right now. We are in this case. So we have a cross section. This width 30. This width, how much? 14. We have area steel here. And this area steel equal, I think, 10 point something, 0.12. Yeah, and 30 and 26 and 4. This depth until this area steel 30 This thickness 4 inch. We are in this case right now. The neutral axis outside the flange. So I'm gonna assume this cross section equal to this part and this part at the top. A little bit of this area steel will be at the bottom. I'm gonna assume it area steel flange. Means this part of area steel working with this flange only. So anybody can tell me what is the length of this width? The total width 30. So if you subtract 30 minus 14, divide 2, this one will be 8 inch and this one will be 8 inch. And the thickness 4 inch. Plus the remaining part of the cross section, we have this part will be here. And the remaining area steel, the remaining will be called area steel web. And this depth will be A. And this width will be 14. Do you agree? Yeah. Do you have any comment, any problems? We have 2 parts. I divided this cross section to 2 parts. And your area steel to 2 parts. Remember, area steel total, which is 10.12, equal the first part plus the second part. Remember, put it in your mind. Okay? Let's start with the first one. We will have compression and we will have tension. And the distance in between tension and compression will be depth minus this thickness HF divide 2. So for part 1, capital C will be 0.85 time F prime C 4000 time, what is the total width here? This one plus this one, how much? This one plus this one, how much? 16. Thickness, what is the thickness here? 4. So I can figure out capital C. Capital T will be this area steel flange time F yield 60,000. So this value will be 60,000 area steel flange. And the capital C will be 0.85 times 4,000 times 16 times 4 equal 217,600 pound. Both of them are equal, so 217,600 equal 60,000 area steel flange, C equal T. So I can figure out the first part of area steel will be 3.62 inches square. This part of area steel equal 3.62 inches square. Can you tell me what is the value of MN? Yeah, equal area steel flange times F yield time distance in between. What is the distance in between? Depth minus H divide 2. Depth minus H flange divide 2. Area steel flange 3.62. F yield 60,000 depth 30. Each flange, the thickness 4 inch, divide 2. I can figure out this number. It will be 6092800 pound inch. We don't like this number, so I'm gonna divide it by 12 and divide it by 1000. It will be 507.7 kib foot. First part. Before starting with the second part, area steel total equal 10.12. Area steel flange for the first part of the cross section 3.62. Can you figure out the remaining area steel? Yes, I can. 10.12 minus 3.62. The remaining area steel will be 6.5 inches square. We have in the remaining part, we have compression here and we have tension here. How much this compression will be? This compression will be 0.85 F prime C time this depth A, this width 14, and F prime C 4000. So I can figure out this number as a function of A. 0.85 times 4000 times 14 will be 47,600 A. We have tension here, capital T, which equal area steel web times F yield. The remaining area steel how much? 6.5 times 60,000. So this number will be 390,000. C equal T. So 47,600 A equal 390,000. The only unknown is A. .2 inch. The distance in between is D minus A divide 2. So nominal moment for the second part will be area steel web times F yield times D minus A divide 2. Go ahead and put your number 6.5, 60,000, depth 30 minus A 8.2 divide 2. So I can figure out this nominal moment for the second part. This one will be this number pound inch, divide it by 12. It will be 841750 pound foot, divide by 1000. It will be 841.75 kib foot. This is the second part. Part number 2. First part give you a nominal moment. Second part give you another nominal moment. The whole cross section will have nominal moment equal nominal moment from the first part plus nominal moment from the second part. So we have 507.7 plus 841.75. So the final answer will be 1349.45 kib foot. But we are looking for design moment. The design moment will be phi mn. So I'm gonna multiply this number by 0.9. Your design moment will be 1214.5 kib foot. It's longer a little bit, but you need to start first to assume if your neutral axis within the flange. If it's within the flange, it will be shorter. That's enough. But if A greater than slab thickness, that means neutral axis outside the flange. So we need to break this cross section to two parts. First part, this overhanging part with another part, working with a little bit of the area steel. Then the remaining part of concrete working with the remaining part of area steel. This little part plus this little part, I can figure it out. The thickness of this part is given, which is a slab thickness. So I can figure out the capital C in concrete. This part of area steel, I can figure out the capital T, but a function of area steel flange. If you equate capital C with capital T, I can figure out this part of area steel. Once you get this part of area steel, I can figure out the nominal moment of this part of the cross section by multiplying capital T by the distance between T and C. This distance equal D minus H flange divide 2. So I can figure out the nominal moment of the first part. Remember, this total area steel equal this area steel plus the remaining area steel. If you can figure out this part of area steel, I can figure out the remaining part. Once you figured out the remaining part with this part of concrete will make acrobium. So we have capital C will be function of A, because I don't know what is the actual depth of neutral axis. And we have capital T, I can figure it out right now. Equate these two equations together, so I can figure out the value of A, so I can figure out the nominal moment of this part of the cross section. Finally, the nominal moment for the whole cross section will be the first part plus the second part. Once you get the nominal moment, I can figure out the design moment by multiplying nominal moment time phi. What do you think? Burak, first part of the cross section with a thickness equal HF, which is 4 inch. But the second part with the neutral axis, I don't know where, so I have A. It's different. Just practice, because you have 13 hours at home, so probably in the exam you will find something like this. You know what I mean? So I don't need to submit the last problem in the homework, but just go ahead and practice. Probably you will find something like this because you have enough time at home. Any other question? Because I have something today, I'm gonna start. Will be more interesting than before. Okay, Alan. The total width, how much? 30? Yes. And this width, how much? 14? Yes. So this part and this part, this width plus this width will be 16. and this one will be 8, and this one will be 8. You got it? Okay. So the total width 30, and this little width 14. So the remaining, this one plus this one will be 16, which is 8 and 8. And the thickness is given 4. Any other question? So guys, this module is very, very long. This one, we learned many things in this file. If we go back, we learned how to assume the cross section. We learned how to assume the concrete cover to figure out the depth of the steel reinforcement. We learned if you have cross section, everything is given. I can figure out the nominal moment and then multiply it by phi to get the design moment. And we learned if the moment is given and the area steel is not given, how can we use table to figure out rho and then area steel? We learned if you have a beam, 2 span, 3 spans, or whatever, with distributed load, I can figure out the moment. And this moment can tell you where I can put the steel reinforcement, the position of steel reinforcement. Okay, remember, please don't do this mistake in your exam. Steel reinforcement at the tension side, bending moment at the compression side. So moment can tell you where is the compression side. That means the tension side will be on the opposite side. Okay, we learned also in this module how to calculate the on weight of the beam and to add this on weight to the given dead load to figure out the ultimate combination and figure out the bending moment. In this module also, we learned what are the types of cross section. We have balanced section, we have under reinforced section, we have over reinforced section. We learned also in this module, we have a different kind of sections. T section, if you have beam connected to slab, the slab will work as a flange to this beam. We have 2 scenarios. Probably the neutral axis will fall within the flange thickness, which is very, 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 very simple. Just a few steps, that's it. But if you are the neutral axis outside the flange, we need to do some stuff. We need to break this cross section to 2 parts, first part and second part. I can figure out the nominal moment for the first part, nominal moment for the second part, finally the nominal moment for the whole cross section. Both of them should be added and then multiplied by phi to get the design moment. This module is very critical. Okay. We have another topic I'm gonna start today and finish it up next time, and it will be included in your exam. It's very interesting. Don't worry, it's nothing new, but something interesting. You will you are feeling that you learned something interesting. Just to start, for any slab, any floor, please go around, watch around you right now in your apartment or in your building. What do you see around you? You will figure out that we have 2 types of load. We have something called dead load. We have something called superimposed dead load. We have something called live load. Let me explain it a little bit. if you pour concrete with a thickness h, if this slab or this concrete has own weight. That's right. Anything in the life has own weight. Even the air has a weight. So concrete itself or a slab itself has own weight. This can be called dead load. So dead load includes the own weight of the slab. Do you think you are living on concrete directly? I don't think so. I believe you have a little bit of finishing. Anything covering the concrete surface can be called finishing with different types, with different kinds. So probably you have ceramics or you have anything, parquet, you have probably you have wood, floor or something. Anyway, we have something called finishing. This called superimposed dead load. Guys, I believe this finishing will stay at the same position. Do you think you can go to campus in the morning if you return it back at the evening to your home? This finishing will get out? No, it will remain on the concrete surface all the time. So it's dead load. It's dead load, but we can call it superimposed, additional dead load beside the own weight of the slab. If you look around you, you will find yourself. You are a life load. Your laptop is a life load. Your desk is a life load. Dining table is a life load. Your bed is a life load. Your chairs, everything for any kind of furniture can be called life load. In 1 minute, you can move your bed outside the building. That's right. You can move your bed from a room to another room. You can move from this room to another room. So you are life load. And all furniture around you are life load. Any question so far? I believe any slab will have these three kinds of load. Dead load, superimposed dead load, and the life load. By the way, I uploaded yesterday a new table. This table called life load. Life load. I'm not sure what you mean by life load. Okay. I will let you know. If you open this file, you will find something like this. For example, if your building is apartment, residential building, and you are using any room as an office, your life load will be 50 pound per square feet, PSF. For example, if your building is theater, lobby in a theater, you are talking about a slab can be used as lobby in a theater. That means the life load will be 100. We can expect too much people or too many people. Another example, if you are talking about building used as a garage, if your slab supporting passenger cars or vehicles only, that means the life load will be 40. If you are talking about hospitals, based on what is the kind of the room, patient room will have a life load equal 40 pound per square feet. So guys, life load can be figured out if you know what is the type of the structure or what is the type of the building. What is the main function of the building? To be more specific, not type of the building, type of function of the building. So I can figure it out. So please, we have a table. This table can give you the uniform distributed life load according to American Society of Civil Engineers, 7 for 2010. We need to follow these standards. Any question for this point? So superimposed dead load is the load of the finishing only. Yes, for example, the title that is sitting on top. Yes. No, not both of them. The finishing only. The finishing only. So we need, remember, we need to add this one plus this one together. And both of them will be dead load. And then this life load will be LL, life load. So we have on weight and we have superimposed dead load. Both of them must be added together. Okay. Okay. By the way, if you would like to consider the on weight of a slab, just thickness of this slab time gamma of concrete. Make sure that gamma of concrete is 150 pound per square feet. Make sure that the thickness in feet. If you multiply this thickness of a slab in feet time gamma of concrete, you can get the on weight of a slab as pound per square feet. Superimposed dead load will be given most of the time as pound per square feet. This life load from this table will be pound per square feet. So the on weight can be calculated. Most of the time will not be given, but the thickness of a slab will be given. So if you multiply this thickness in feet, remember, in feet, time gamma concrete, which is 150. I told you before, remember this number. Gamma for concrete, normal weight concrete, 150. So I can figure out the on weight pound per square feet. Superimposed dead load, most of the time it will be given based on the type of finishing. Life load, you can figure it from this table based on the type of function of this building. Also, pound per square feet. We have something called tributary area. Tributary area. What you mean? I believe I covered this before, if you remember, in structure analysis and the design course. We have a beam like this one. And we have another beam like this one. And we have another beam like this one. Each beam will support load from center line to center line. So the first beam, this one, will support this part of the slab. The second beam, which is this one, will support this part plus this part also. And the third beam will support this part only. So what is the width of a slab supported by the intermediate beam will be this part, this width. Do you agree? We covered this before, I remember. So if you have a beam, you have another beam, you have another beam, you have another beam, please Go ahead and draw center line between each beam. So if you are talking about this beam will support this width of the slab. Anything on the slab on this area will be supported by this beam. Do you agree? Do you have any question regarding this point? Okay. Okay. Remember and put it in your mind. If you have simply supported beam, one span only with uniform distributed load, your moment here will be WL squared divide 8. If you have two span, do you remember? We will have negative moment here. And your moment looks like this. Do you remember? This value will be WL squared divide 24. This one will be WL squared divide 9. WL squared divide 14. WL squared divide 14. WL squared divide 24. If you have more than two spans, we will have negative, and we will have negative here, and another negative here, and keep going. WL squared divide 24, we covered this before. I just remind you, 14, WL squared divide 10, WL squared divide 11, WL squared divide 16, and so on. Remember, one span, two span, or more than two span, 3 or 4 or 5 or 6. Okay? And remember, any beam will support a width of the slab from center line to center line. Remember, any slab will support three kinds of load. Please put your hand on them before starting any problem. Dead load, which include on weight of a slab equal the thickness of this slab in feet time gamma concrete. Superimposed dead load, try to figure it out. It should be given. And we have life load, probably the life load, if not given, search in the problem. What is the type of function of this building? Is it hospital, garage, residential building, or whatever? Then open the table to figure out the value of life load as pound per square feet. So please put your hand on these three values. Once you put your hand on these three values, remember, we have W ultimate equal 1.2 dead load. Dead load will be this one and this one, plus 1.6 times life load, which will be this one. Once you submit this answer or this question, this equation, I can figure out the uniform distributed load on the beam. Each beam will support this width. So if you multiply this load by this width, finally you have a beam with distributed load. If this beam one span, here is your moment. If this beam two span, here is your moment. If this beam more than two span, here is the moment. Once you get your moment, I can do some design. And I will cover these two examples next time. We have very important examples.